Today I'm going to talk about our system absence, usage-based failure detection in mobile network. This is a joint work with AT&T Lab Research, and this work doesn't reflect or describe the AT&T network. So in the current mobile networks, despite that there are redundancy and monitoring system deployed, there are still failures that are not detected by any monitoring system. We call those silent failures because they are not aware of by the network operator. And silent failures happens, for example, when a new service rolls out and the monitoring system is not equipped to detect those failures, or when a bug happens on a firmware, and when the device is updated the firmware, it will not be able to access the network as normal. Unfortunately, the silent failures are very difficult to detect. In passive monitoring, passive network monitoring, the network is monitored for failures events, and because the dynamic in a mobile network, events like dynamic load balancing, maintenance activities, or dynamic routings happen frequently. This could cause drops on traffic or usage on network element. However, these drops do not imply service disruption on the user side. For example, in this figure, we can see that even though the actual load on an S gateway node, a serving gateway node, significantly lower than the expected load when a load balancing events happen, this load was shifted to another S gateway node in the same pool, and the user were not impacted. Key performance metric indicator or KPIs can also be used for event detections. However, similarly, KPI may not reflect service problem on the user side. For example, accessibility KPI may still look good even when only a subset of users can access the network. So somehow counterintuitively, a healthy network from the monitoring perspective does not imply good service experience on the user side. In active service monitoring, the test traffic will be sent across the network to all possible service paths for event detections. However, consider a large amount of device types, device makes, and applications service, and a huge country with many geographical locations to probe. This is not scalable to use active service monitoring. And a network can also rely on customer usage, customer feedback to notify the failures in the network. However, relying on customer feedback is not reliable, is not desirable, and is typically slow. The reason is when the customer feedback arrives, this means that the impact already happened, and it takes time for the feedback arrive at the network. For example, in this figure, we can see that there are about 3.5 hours of delay for the customer feedback to get back to the network. So we propose our system absence. That is a passive service monitoring system that monitor customer usage for events detection in mobile network. So we argue that absence of customer usage is a reliable indicator for service disruption in a mobile environment, in a mobile network. The key ideas behind absence is very simple. We monitor the usage of a group of users in the network. If the network is good, we can observe a good usage from that group of users. If a problem happens, either in the network or on the user device, the user will not be able to use the network as they normally would. If only a few user experiencing problems, maybe the usage we observe from that group will look normal. However, if a large number of users observe the problem, they will not use the network as they normally would, and so the usage of that group of users will significantly reduce. And by monitoring the usage, we saw a drop on the usage, and we can imply service problem. So this method can detect both hard failures like outage or performance degradations on the servers. So this is how Absent works. Absent use anonymized aggregated core detail record or CDR to extract usage from user. So CDR is collected in real time in many operators. They are readily, it is readily available for multiple services like LTE, voice, SMS, etc. And they are, and it is basically capture the usage of the user. For example, when you make a call, a CDR record will be generated in the network, and so Absent use CDR to extract the usage from a group of user, and it's then use the historical usage to build a predict usage of that group, and if the current usage is significantly lower than the expected usage, Absent will detect that as an anomaly. So Absent intuitively makes sense. However, we don't know whether Absent is feasible or not, because we don't know whether usage is predictable enough for anomaly detection. So intuitively, usage of a individual user is not predictable. For example, I'm going to work today, I make 10 calls, but tomorrow I'm going on vacations, I don't make any calls at all. So my usage is not predictable. However, if we look at the usage of a group of users, the usage is more predictable. These two figures show the 3 weeks usage of two different groups. On the left hand side, we have a smaller group with 70 users. On the right hand side, we have a larger group with 3,000 users. As we can see that the smaller group, the usage is not predictable. However, the large group, we have the usage is more predictable and more suitable for anomaly detection. So the answer is yes, if we usage is predictable if we have a large enough of user, a large enough group of user. And then Absent have to deal with challenges to be more efficient in detecting service problem. So for example, a failure in a mobile network could happen to multiple scopes. For example, it could happen to a geographical area, it could happen to a specific service or specific device types, device models. How can we design Absent to detect failures that happen to multiple dimensions? And given that we have a very large network with multiple dimensions to monitor, how can we scale the system? And how can we deal with user mobilities in a mobile environment, because users are moving? And how can we improve predictability of the usage for better anomaly detection? So in this talk, I will focus on the first point and touch a little bit on the second point, and the other 2 points you can find it in the paper. So because of the deployment of a mobile network, failures happen in a localized manner. For example, it could happen to a group of users that are very close, geographically close, or it could happen to a set of devices that have specific hardware and software settings. So we utilize the zip code hierarchy to divide user into different geographical locations. And a user can belong to multiple zip code, multiple geographical location in the same time. For example, I can belong to the group of all users in Salt Lake City, and in the meantime, I can belong to the group of all users in Utah, for example. And under each geographical group, we further divide the user into different groups based on their OS, on device type, device model. So by combining the two hierarchies, we can flexibly group user. For example, we can have an aggregation as large as all Android devices in the US, or we can have an aggregation that as small as all iPhone 6 user in Salt Lake City, for example. So let's look at Epson system design. Epson will maintain a historical usage for each aggregation of user. It then wakes up every hour to extract the usage of that group from the CDR, and then it will append the usage, the last hour usage, to the historical usage, and then the result is we have a current time series usage, and that time series will be fed into a event detection module for alarms detection. So interesting point is the spatial aggregations given is it have a scalability issue, because in a mobile network with millions of users, there are millions of transactions every hours with gigabytes of data every hour. So, and it have multiple dimensions like geographical locations, device mix, device model, service type, etc. So how can we make this one more scalable to the entire network? Fortunately, CDR could be processed independently, so we utilize MapReduce to speed up the spatial aggregations. And currently, Epson is running on a Hadoop cluster with 100 Hadoop nodes, and we found that it can scale up to very small aggregation like device make, like or iPhone 6 device under a zip code area. So yeah, we found Epson is responsive in an operational environment. The event detection algorithms will decompose the user's time series into the three components: the trend, the seasonal, and the noise. Trend is basically the moving average of the time series. The seasonal is basically the average value of phasing values across seasons, and the noise is the rest, the usage time series subtract the trend and the seasonal. So we pay special attention to the noise for anomaly detection. So basically, we compare the noise component with the lower 95% confidence interval of the predicted noise component. If the current noise component is lower than that lower 95% confidence interval, then Epson will detect that as an anomaly. For example, in this case, we have 2 drops in the usage time series, and that's corresponding to 2 anomalies in the noise component. So how can we evaluate such as a system, right? So we use 6 months of CDR record from a real operator, and then we introduce failures into that CDR to mimic network failures and device failures. So we have 11,000 failure scenarios that uniformly covers 6 different parameters in the network of the failure. For example, with 11,000 failure scenario, we can have a failure that happened to a very large aggregation. For example, all device in Los Angeles, or it can the failure could happen to a very small aggregation like all iPhone device in downtown Los Angeles, for example. And then we use detection rate and loss ratio as the metrics for evaluations. Detection rate basically is the ratio of the amount of events we detected over the amount of events we introduced. And the loss ratio is basically the ratio between the total usage get lost when before we detected the event divided by the normal usage during that event. So this figure shows the overall detection rate for absence. On the x-axis we have a failure impact. On the y-axis we have detection rate. So as we can see that absence works pretty well for events that have a large failure impact. For example, it can detect more than 96% of events that have more than 15% of impact, and it doesn't work that well for failures that are not very impactful. For example, less than 10% of usage. And the reason is absence may treat those events that are less impactful as a normal variation in user usage. So this CDF shows the loss ratio of all detected events. Basically, we can see that 98% of the detected events will be detected after only 10% or less of usage get lost. So this means that absence is pretty responsive in detecting events. So we also evaluate absence against a set of known failures in a operator, and basically we can absence can detect all of the events with 100% true positive. We also interest in the alarm rate, which is the amount of alarms that absence will generate every day, because in an operational environment, a system that generates the alarms that the alarms have to be invested by a operation team, and to make a system practical, the amount of alarms have to be small enough, reasonable enough for a operation team to look at. And so in absence we can use a cut-off threshold to filter out small events that are less impactful and only review large events to the operation team. So as we can see that, and because of the proprietary reason, we cannot review the cut-off threshold, the exact number of cut-off threshold, and the alarm rate. So we anonymize them as N and M. So as we can see that if absence use for N as a cut-off threshold, it can detect all of the events, and in the meantime, it only generate a alarm rate as M, about M. And we confirm that M is small enough and reasonable enough for a operation team to handle. So that is so absence is practical in an operational environment. So in conclusion, we introduce our system absence that detects failures in a mobile network using customer usage. We found that it is efficient and practical. Also, thank you. I'm happy to take questions.
Thank you.